Everyone, and thank you for joining me today in this Studium Generale session about A Brief History of Time, the best-selling book by Stephen Hawking. I'm Elisa Chisari. I'm an assistant professor at the Institute for Theoretical Physics at Utrecht University. And today I'll be telling you about the book, but also I hope that by the end of this lecture you will also have learned something about the scientific contributions of Stephen Hawking in describing the universe that we live in. So, Stephen Hawking had a remarkable life. He was born in Oxford on the 8th of January of 1942, on the 300th anniversary of the death of Galileo. His mother had studied economics, politics, and philosophy at Oxford, and his father medicine, and both were very strong figures in his life, encouraging him to pursue higher education. He was not particularly hardworking, you might be surprised to hear, but he was very insightful from a very young age, and so much so that his schoolmates nicknamed him Einstein. He completed a degree in theoretical physics at Oxford and moved on to a PhD at Cambridge in 1962. By that time, he had already been diagnosed with the fatal disease that would accompany him for the rest of his life, and the doctors implied that he only had 2 years to live, and so he resolved to do something really creative with the remaining time and aspire to tackle some of the most fundamental questions in physics. Little did he know that he would live till the age of 75 and be remembered as one of the brightest minds in the field. He passed away on March 14, 2018, on the 139th anniversary of Einstein's birth. He left a tremendous legacy behind, which included the best-selling popular book, A Brief History of Time, but also many others, and TV appearances that have made the field more accessible to the general public. So today's presentation is meant to be a modest tribute to his legacy. One of his most recognized pieces of work is, of course, this book, which has inspired many generations to ask their own questions about the nature, origin, and fate of the universe. This is, of course, A Brief History of Time, here in Spanish, the edition that I read as a teenager. It was an ambitious piece of work, and it covered in simple terms the laws of physics that govern both the smallest and the largest scales of the universe. And I want to quote the words of his editor, Peter Goodsardi, who said, "The manuscript was a slender but extremely dense 100 pages, describing the quest for the holy grail of science, one theory that could unite two separate fields that worked individually but wholly independent of each other. Particle physics explained the ghostly forces at work within atoms, whereas astrophysics made sense of massive effects like gravity that operated at the level of galaxies and star systems." The book was first published by Bantam Books in 1988, and it became an instant bestseller. Over the next 20 years, it sold 10 million copies, and it was translated into 35 different languages, which is why I was lucky enough to have an edition in Spanish. So in today's presentation, I'll try to do the book justice by following a similar style. We'll start by constructing a model of the universe and then go back in time to ponder about its very beginning. This is covered in chapters 1 through 3 of the book. We'll see how Stephen Hawking contributed to shaping this model of the early universe through his own research. The second topic that you see here is the nature of black holes. Black holes are very special objects in the universe. They are so dense that nothing, not even light, can escape from them. And while black holes were first predicted by the general theory of relativity, which is due to Einstein, we will see that Hawking made very relevant contributions in this field. To do this, he had to borrow elements not only from general relativity, but also from another physical theory, the theory that applies to the smallest scales in the universe, and this is quantum mechanics. Both theories need to come together if we want to explain the nature of black holes, and this will be covered in chapter 4 through 7 of the book. Now, surprisingly, the two phenomena are connected, and chapters 8 through 10 of the book make that connection clear. Our models for the beginning of the universe are actually not that different from the models that we have for black holes. We can describe them in pretty much the same way. And you'll be surprised to hear that the beginning of the universe is like the collapse of the black hole, running backwards in time. And I want to conclude then the presentation by giving you a picture of current research in cosmology in the study of the universe today. So with that, let's get started. So let's go to the very beginning. To talk about our model for the universe and understand its very beginning, we need to go back in time in our own history. In the 6th century BC, the Greeks started asking the first questions about the nature of our universe. They were the first to go beyond acceptance and into inquiry. These philosophers tried to understand the components and the structure of the universe. They were responsible, in particular, for the idea of atomism. Eusebius and his student Democritus made the thought experiment of splitting a stone. So imagine a stone that you split with a sharp knife ad infinitum. So you split it in half, and then again in half, and then again in half, forever. It was impossible to think that this process could continue forever, and this led them to the thought that there must exist some indivisible unit of matter, which is called an atom. According to this view, everything in the universe is made of atoms, and aggregating them in different ways resulted in the familiar properties of matter, such as color or smell. Atomism triggered a number of consequences. The idea gave rise to the thought that there were indivisible parts in any kind of magnitude, geometrical extension over time, for example. And if the universe was all made of the same units, then the Earth must be no different to other celestial bodies. This implied, for example, the existence of other worlds. Democritus even proposed that there were mountains in the moon and that our galaxy was an aggregation of stars. He concluded that space was infinite and that it consisted of empty areas and collections of atoms in between. So these were the early times. Now, today, as we point our telescopes to the vast universe, we can see that empty space is dotted with billions of galaxies. Some of them are just like our own, but they come in a variety of shapes and sizes, as you can see in this picture. The picture that we reproduce here is an ultra-deep field taken by the Hubble Space Telescope. In this field, which is just 11 square arc minutes on a side, there are 10,000 galaxies. So this is a tiny area of the sky, and there are 10,000 galaxies. Each of them is home to billions of stars, which are in fact made out of atoms. Today, we know that the atoms are not so indivisible as the Greek would think. They are really composed of subatomic particles, which are, in turn, made out of further smaller particles, which are quarks and leptons. Now, a further revolution occurred in the 17th century. The invention of the telescope by Galileo allowed him to make the observations necessary to support the heliocentric model, while at the same time cementing the idea that our universe could be populated by many worlds. He was able to see mountains on the moon, suggesting that this was not a perfect sphere, but rather a complex geological system, like our own Earth. He also discovered 4 of Jupiter's moons and described their motions. He resolved areas of the sky that turned out to be populated with many, many stars, and found that many more were observable with the power of his telescope. With the advent of the telescope, many embarked in making maps of the heavens. Soon, some special regions were identified and called nebulae, like the one that you see here on the left. These were fuzzy clouds in the sky whose origin was unknown. Were they objects in our own Milky Way, or were they islands of stars like our own Milky Way, but much further away? Today, we see these fuzzy clouds in all their glory. They are extragalactic objects, and we can obtain exquisite images of them with ever more powerful telescopes, which in some cases even allows us to resolve individual stars in these galaxies. But the question of whether these so-called nebulae were in fact extragalactic would remain open until the 1920s. Edwin Hubble, an American astronomer, arrived at Mount Wilson Observatory in 1919, just in time to make use of the largest telescope in the world, the Hooker telescope. He measured the distances and velocities of galaxies and determined an astonishing relation, which you can see in this figure from his original work. Galaxies that are further away from us are moving away from us at greater speeds. So you see here the galaxy distance on the x-axis and the velocity on the y-axis, and larger distances correspond to larger velocities, which is the line that is depicting the relation between them. Now, Hubble's work cemented the idea that the universe was expanding. This new conception of the universe was revolutionary in that it went against the idea of a steady-state universe, which was the prevalent theory at the time. So in a steady-state universe, the universe is neither expanding nor collapsing, while in the expanding universe, you can see how distances between galaxies grow bigger with time. Now, this theory, the steady-state theory, was so well accepted that around the same time of Hubble's observation, Einstein himself modified his general relativity theory to ensure that the universe did not expand or contract. This would turn out not to be the case, that the universe was actually expanding. So let's turn now to Einstein's theory. In this theory, gravity is a consequence of the deformation of a space-time by massive objects. The denser the object, the higher the curvature of space-time that it produces, and the stronger the gravitational attraction. So you see here 3 objects of different masses. We've got the yellow, the brown, and the red. And the yellow one, which is the most massive, is changing space-time in a more drastic way than the others are. And for this reason, other objects will be attracted to the yellow one more strongly than to the red or the brown one. Now consider the following experiment. You're standing on Earth and throw an object up in the air, vertically up. And you know by experience that this object will end up reaching a certain height and falling back to you. This is, of course, a consequence of gravity. Now, in Newton's theory, the original theory for gravity, developed in the 18th century, gravity is a force acting on an object in the same way that you might pull or push from something with your own hands. In Einstein's theory, this is no longer true. Gravity is the result of these dips in the fabric of space-time. What is certain is that you would have to imprint a very large velocity on this object that you're throwing up if you wanted to escape from Earth. This is, of course, possible. You can do this because we routinely send spaceships from the Earth to the other regions in the solar system, or we put satellites in orbit. But in order for them to escape the gravity of the Earth, you need to be traveling vertically up at a speed of 11 kilometers per second. So that is a lot of fuel. The situation is even worse if we consider more extreme objects in the universe. To escape from the gravity of the Sun, you need a velocity of 618 kilometers per second. But traveling at that speed, you would not be able to escape from a neutron star. There are objects called black holes from which not even light can escape. So no matter what speed you give to something inside a black hole, it would never be able to escape. Light travels at a finite speed of 300,000 kilometers per second, and that's at the fastest speed that we think can be achieved by any moving object. But this is not enough to overcome the gravitational pull of a black hole. Black holes are an extreme example of the curvature of space-time, where the density is so high that not even light can escape. A black hole forms when a star that comes to the end of its life cannot support its own weight, and it collapses into a singularity. And what is a singularity? It is a point in space that contains a huge mass in an infinitesimal so tiny, tiny space. And in this region, the laws of physics as we know them, they cease to be valid. So after this slight detour into general relativity and black holes, let's now go back to the idea of the expanding universe. The realization that the universe was expanding left scientists wondering about what the early universe would have looked like. Clearly, if it's expanding, then it must have been denser at early times. But how do we describe this scenario? Stephen Hawking realized that he could describe the beginning of the universe by using what he knew about the collapse and formation of black holes. The expanding universe could be modeled as a collapse of a black hole played backwards in time. If we go back in time far enough, we would encounter a singularity in the same way that we encounter one at the center of the black hole. But there's more to Hawking's theory. He also suggested that time actually began with the singularity, and there's no meaning to the concept of time before that. So to summarize this part, Hawking's proposal stated that the universe had a beginning. It began with the singularity, and that time began with the Big Bang itself. The first observational evidence for the fact that the universe had a beginning came in the 1970s with the discovery of the cosmic microwave background. This is radiation, so light, left over from the Big Bang, which was visible 400,000 years after the Big Bang. So 400,000 years after the Big Bang, this light started traveling to our telescopes, and we still see it today. Of course, it's not very bright, but we still see it today with our instruments. And we can map this radiation out very accurately, and this is what you see in this picture. So the fact that this radiation was found proved that the universe had been much denser and much hotter in an early period. And this gave support to the idea of a beginning for the universe, which Hawking was involved in proposing. So for now, let's dig deeper into black holes to understand the importance of another of Hawking's proposals. So today, we have direct evidence of the existence of black holes. In 2019, the Event Horizon Telescope released the first direct image of a black hole, which is the one that you see here on the screen. Meet the black hole in galaxy M87, 6.5 billion times more massive than the Sun. What you see here is a black disk surrounded by luminous material. The disk is the black hole itself, and the size of the disk corresponds roughly to the region from which light cannot escape. The luminous material around it is matter that is around the black hole, and it's succumbing to its gravitational pull, and it glows because it is very hot as it approaches the black hole. It gets very hot. What a fate to plunge into a black hole to never escape. But is it true that escape is really impossible? To understand how Hawking could stage an escape from a black hole, we will have to use another one of the famous physical theories. This is the theory that describes the smallest scales in the universe, and it is quantum mechanics. One of the basic principles for quantum mechanics is Heisenberg's uncertainty principle. Heisenberg's uncertainty principle tells us that we cannot know the position and the velocity of a particle at the same time. If you know how fast you're traveling, you will not know exactly where you are. If you know exactly where you are, it must be because you're standing very still. So consider the following analogy. We have a bug in a dark room, and we don't know it's there. We want to turn on the light to see it, but when we do it, it runs away. And so if we really want to know where the insect is, we'll have to catch it. In doing this, we'll have to modify its position and its velocity. So one of the consequences of Heisenberg's principle is that there's no such thing as empty space. There's always the potential of having a bug in your empty space. What this means in practice is that in the vicinity of a black hole, particles are constantly being created and annihilated. And these particles come in pairs, a particle and its antiparticle. Hawking realized that on occasions one particle falls into the black hole while another one escapes. The collection of particles that escape are given the name of Hawking radiation in his honor, and there are some profound consequences to the idea that the black holes can actually emit this radiation, emit these particles. So what are the implications? So first of all, black holes can emit particles. And this is bad news for the black hole. For the particle in the pair to be emitted, the antiparticle that falls in must cancel some of the mass inside of the black hole. And if this process continues over time, the black hole can eventually evaporate and disappear. But most importantly, the efforts made by Hawking in understanding the black hole environment allowed the community to make progress in one of the most important unsolved problems in physics today. How can we unify the equations, the models that describe the theory of general relativity with quantum mechanics? When you try to write them together, to write one expression for both of them, that doesn't work. And in the words of his close collaborators and Nobel Prize winner Kip Thorne, we remember Newton for answers, we remember Hawking for questions, and Hawking's questions themselves keep on giving, generating breakthroughs decades later, when ultimately we master the quantum gravity laws and fully comprehend the birth of our universe. It will be by standing on the shoulders of Hawking. So in other words, this discovery that black holes emit radiation was also progress for developing the unification of general relativity and quantum mechanics, because in describing this phenomenon around a black hole, Hawking had to make use of both theories. And the quest continues. And in this part of the talk, I would like to tell you a little bit about research in cosmology today. So one of the focuses of Stephen Hawking's research was the origin of the universe. And he would not shy away from this question despite its difficulty. He thought science should be able to tackle it, and evidence to support the idea of a beginning to the universe would come in the 1960s. Two radio astronomers, Penzias and Wilson, were testing a new antenna that was being used to attempt to communicate with an artificial satellite. Their efforts were undermined by a constant hiss in the signal of unknown origin. This noise seemed to be coming from all directions, and it did not change throughout the year. They were puzzled as to the origin of what seemed to be noise in their detectors. At the same time, a group at Princeton University had been working on models of the early universe and had made a prediction of a cosmic microwave background, radiation that would be left over from that time and which should be within the reach of radio telescopes. So Penzias learned about this prediction, and the discovery was soon made public. Penzias and Wilson got a Nobel Prize for their discovery in 1978, and new experiments followed that provided more accurate measurements of the cosmic microwave background. And so the image that you see here, which we've seen before, is the most exquisite picture yet of the cosmic microwave background, taken by ESA's Planck satellite in the last decade. And what you're seeing are tiny fluctuations in the temperature of the gas that was our universe 400,000 years after the Big Bang. The fact that we can detect this radiation comes as evidence that the universe had a dense and hot beginning. While the discovery of the cosmic microwave background gave support to the idea of a beginning to the universe, it also opened new questions. The patterns in the map encode information about the composition of our universe, and they revealed a striking picture. As you can see in this graph, the matter that you can see and touch is only 5% of the universe that we see. The rest is in the form of dark components. So these are dark matter and dark energy. And we don't know what these components are made of. There are theories and there are proposals, but nothing is for certain at the moment. So we continue to explore the nature of these components. Dark matter comprises 27% of the energy density of the universe today, and without it being present, galaxies would not have had enough time to form and we would not be here. Dark energy is a mysterious force that we think is responsible for the acceleration of the expansion of the universe, and it makes up 68% of the energy today. The nature of dark matter and dark energy remains one of the biggest open questions in cosmology today. And so in order to answer these questions, cosmologists are going beyond maps of the cosmic microwave background to map the galaxies that grew out of the gas present in the early universe. Every point that you see in this picture represents a galaxy that we have mapped. Galaxies depicted in blue are closer to us, and galaxies in red are further away from us. The bright area in the center of the map is our own galaxy, which blocks the view in certain directions. Much information can be extracted from this distribution of galaxies. One of the aims of these campaigns is to pin down the expansion history of the universe to unprecedented accuracy. By analogy, you could think of this as revisiting Hubble's measurements, but on a much larger scales, and with millions, even billions of galaxies over a large part of the history of the universe, rather than a couple dozens. And we will know, after we make these measurements in more detail, how the universe is expanding. And we will not only count these galaxies and measure their speeds, but we will also measure other properties such as their shapes, which will allow us to shed light on the nature of dark energy and dark matter. We built these maps of the sky with dedicated telescopes, which spent most of their time over a number of years mapping every accessible region of the sky. They built mosaics of photographs, which can then be used to identify and catalog all visible galaxies. An example, which I show here, is the VLT survey telescope at Cerro Paranal in Chile. And this is a state-of-the-art 2.6 meter telescope equipped with a massive camera, 268 megapixels, which can cover an area of 4 times the full moon in any given picture. One of the surveys or maps of the sky performed with this telescope is called the Kilo-degree survey, led by Leiden University in the Netherlands, but with participants all over the world. The Kilo-degree survey is one of a few experiments that are helping map the sky to improve our knowledge of dark energy and dark matter. In the near future, we will see even more powerful experiments come online. This is the Vera Rubin telescope in Chile. It will start operating in 2021. It is expected to cover half of the sky over 10 years, and it will visit each region of the sky 800 times. The fact that the telescope and camera system are new, have a new design, it means that we'll be able to catch more light more efficiently, and this will allow us to increase the sample of our galaxies from the millions to the billions. But not only that, the fact that we visit the sky, each region in the sky 800 times, means that we can make a cosmic video. And with this cosmic video, we can catch transient phenomena such as stellar explosions, which are also known as supernovae. This undertaking will allow us to map dark matter, characterize it together with dark energy, and narrow down the possible theories that could be responsible for these dark components. Now, I would like to close this lecture by taking a step back and looking at the picture of the universe that we have described. According to Stephen Hawking, the universe had a beginning, which is to the left in this graph. It began with a singularity, much the same as we can encounter at the center of a black hole. Then the early universe expanded, and this expansion was like the collapse of a black hole in reverse. As the universe expanded, it cooled down, and 380,000 years after the Big Bang, the cosmic microwave background was emitted. And today we can still map it to learn about the universe's beginning. From that point onward, the pull of gravity made the gas that was present at the time of the cosmic microwave background collapse and form the stars and galaxies that we see today. Today, in the distribution of galaxies, we can recover patterns that allow us to put to the test the mysterious nature of dark energy and dark matter. Hawking's contributions in this field have been enormous. We summarize them again in closing. Based on the theory of general relativity, Hawking showed that the universe must have had a beginning at a singularity, and that time as well had a beginning. It began with the Big Bang. The beginning was like the collapse of a black hole run backwards in time. And black holes are very special objects in the universe. Hawking found that they can emit radiation despite them being black, and they can eventually evaporate. The phenomenon of Hawking radiation paved the way for the understanding of how to unify the laws of physics. So in the words of Stephen Hawking, we don't have a complete picture, but I like to think that we may not be far off. So thank you for joining me. And if you enjoyed this lecture, here are a couple of books and links that you might enjoy as a follow-up reading.